So good morning everyone, welcome to Turbulence again. Today we are going to continue the chapter on turbulent viscosity models. Hopefully we'll finish that chapter and introduce a new chapter. Where we left off last time was here, where we talked about the turbulent kinetic energy model, the so-called K model, with the specification of mixing length Ln. And we showed you the closed form of the equations required to put this model together. We told you it's a one equation model because the only serious equation is the first one, 1021. Right? This is the only serious equation, and I said we reserve the term equation for a differential equation that requires a numerical recipe. These other equations are just simple equalities which I can plug and play if I want to. So really this is the only substantial equation. So this is also known as the one equation model, if you will. So let's write here, one equation model. So today I'm going to introduce to you another model which is two equation model known as the K-epsilon model. How many of you heard of this model, K-epsilon? Raise your hand. Before. This is probably the most widely used turbulence model out there. It's optimized in many different smart ways, so it generally works for a lot of problems and gives you a practical answer. However, sometimes it fails horribly for given types of problems. So you have to be very careful where and when to use it. So it's a two equation model. And in the previous chapter, we said it's a complete model. Meaning that none of the equations depend on flow specifications or discretization. In other words, whatever discretization or flow situation I may have, the equations are the same, they're intact, they don't change. So the K-epsilon model is among the most popular turbulence models, particularly within the engineering community. I mean, most thermofluids engineers have used this, or water engineers, renewable energy engineers. The gist of the work was developed in the 1970s by Launder and Spalding, and this paper I'm citing is one of the mostly cited papers in the literature. I mean, over many thousands of citations have been given to this paper. It's a two equation model because you have one equation for K, turbulence kinetic energy, one equation for epsilon, dissipation rate. The two unknowns in this case are the turbulent kinetic energy K and dissipation rate epsilon. From these two unknowns and equations, any other quantity can be calculated. For instance, a length scale in turbulence can be formulated as K to the power of 3/2 divided by epsilon. A time scale can also be calculated. K divided by epsilon. You might think of this as length scale of eddies and time scale of eddies. It can be calculated. Also, turbulent viscosity can be calculated by these two numbers. So nu T is equal to some constant C, K squared divided by epsilon. So the model is very nice because given two parameters, I can calculate any physical quantity in the flow. Since all quantities can be formed, only as a function of these other two quantities. That is why we say the model is complete, because there's no other term. And whatever the discretization, whatever the mesh, for example, mesh could be a coarse mesh, could be a fine mesh. It doesn't matter. The equations are the same. Also, there is no requirement to specify mixing length, right? LM. It's not required anymore, which is another advantage. Remember, specifying LM depended on the flow last time, and it depended on the type of numerical grid I may have. So it's mathematically nice to put together. We provided you the transport equation for turbulence kinetic energy already, so that was the last page. So that equation is the same. It's not any different in this model. But what's different here is turbulent viscosity is defined, as I said, using this relationship, and then C mu is a new constant, which has been fitted for the model. So this is one of the 5 constants required for this model. Again, there is no way to prove that C mu is 0.09. This was just fitted. It was a very rigorous statistical analysis and fit that was found to work with most flow conditions. However, for epsilon, we do have an equation. And here it is. But the surprising fact is you can somehow derive a transport equation for K, but you cannot derive a transport equation for epsilon. So this is really only an empirical equation. So we are saying that like kinetic energy that could be advected, diffused, consumed, generated, and so on, so can dissipation rate be transported. Right? Like here you see rate of change of dissipation rate, storage of dissipation rate. Here you see advection of dissipation rate, and so on. Okay? Flux divergence of dissipation rate, production, dissipation, and so on. So you have to accept this with somehow a grain of salt. There's no proof, and if you like, this equation is an invention. Okay, that's the best that was done to put it together. There are even many forms of the K-epsilon model out there, where people, change constants and add or drop a term. They formulate some terms, close some terms slightly differently. But the equations that I gave you were the equations for the standard K-epsilon model. And the model is fully closed by a specification of 5 parameters. Okay, and here are the 5 parameters. So really, there are only 5 arbitrary constants required to close the model. Everything else is a transport equation. So what are these constants? This constant C mu, 0.09, C epsilon 1, 144, C epsilon 2, 192. Turbulent Prandtl number for the kinetic energy, usually assumed to be 1. And the turbulent Prandtl number for the dissipation rate, assumed to be 1.3. This is a fit. You cannot prove any of these. This is just the best fit. You might find a lot of papers out there that they tune these constants for different applications. So that is the end of the content of this chapter. Let's do an exercise, and hopefully the material will settle in better. Any questions? So feel free to slow me down at any point.
What is it?
Sorry?
What is sigma epsilon 1.2.
Sigma epsilon?
Yeah.
Yeah, this was another one of the constants in the model. It is just, it appeared in the dissipation rate. It's a good question, dissipation rate equation. Remember that if you have turbulent viscosity, that's just a constant of proportionality for the down gradient hypothesis or diffusion hypothesis, right? But turbulent viscosity only works for momentum. If I want to use gradient diffusion hypothesis for, let's say, heat, temperature, right? Then I would have gradient of temperature here, and I would have to use the Prandtl number for temperature. If I'm using gradient diffusion hypothesis for kinetic energy, right? Now I have gradient of K. So I have turbulent viscosity now divided by the Prandtl number for the kinetic energy. So you kind of scale the constant of proportionality, nu t. You are scaling nu t. So you are assuming a larger constant of proportionality or a smaller constant of proportionality for the down gradient hypothesis. So here too, for epsilon, so you're using the down gradient hypothesis for epsilon, right? It's a flux divergence term, gradient of epsilon. So you need to use the appropriate scaling factor for the constant proportionality, also known as Prandtl number for dissipation rate. Be careful, this is not for heat, it's for dissipation. It could be dissipation rate, it could be kinetic energy, and it could be for heat. If you remember, for passive scalar, we said this was a Schmidt number, right? So there's a lot of these for all variables of interest. Let us do question number 4, and this is somewhat involved. It may take 5-10 minutes maybe, but I really want to take it slowly and derive this for you. So question number 4. An atmospheric scientist wishes to develop a transient one-dimensional momentum and turbulent kinetic energy transport model. She closes the turbulence model by assuming turbulent Prandtl number is equal to 1 and parameterizing a mixing length that also formulates the turbulent viscosity and the turbulent kinetic energy dissipation rate. So suppose that she uses the Cartesian coordinate system, x and y and z, velocities corresponding to these are u, v, and w. So she's using the Reynolds decomposition. So any component of momentum is decomposed into a time average and a fluctuating part. Further, she assumes that mean flow is only in the x direction parallel to a surface, and that z is normal to the surface. So this is sort of like a wall flow. Right? Flow is going over the surface on the x direction, and normal to wall is z. So she assumes mean velocities in x and y directions being 0. Actually, this should be z and y direction be 0, i.e. v and w are 0. So y and z, in fact. So v equals w is equal to 0. In addition, she assumes that the mean velocity u in the x direct or y direction does not change. Okay? So that means u is horizontally homogeneous. This flow is going this way. U is the same as here, as here, as here. And the same as here, as here, as here. So horizontally homogeneous. But if you move away from the surface, u may change. Also, she assumes that the modified pressure has a constant gradient in the x direction. Remember, for wall flows, it was the pressure gradient that drove the flow. So there is a horizontal pressure gradient. And then this is the equation that she comes up with. So this is the closed form of the turbulence model, and we want to derive this. Okay. Basically, the first equation is the momentum equation, because you see the variable of interest is u. Some other terms we'll find out. The second equation is the turbulent kinetic energy equation. So this equation is written for K. And these are the remaining closed parameters. So you see turbulent viscosity is closed as a function of K-Lm, using length and constant Ck. Dissipation rate is closed by the same quantities, although raised to different powers. And mixing length is closed as a function of distance away from the wall. So you see kappa is the von Karman constant, and z is distance away from the wall. This L naught is another constant of the model. So let's derive this. Although I have to do justice to reading the question in full. In the above, identify the momentum and turbulent kinetic energy equations. Well, I already said, momentum equation is the first one, because you got U here. Kinetic energy equation, turbulent kinetic energy equation is this equation. So I've done that part. But you will see I will identify for you these terms as I derive. I will identify the storage term, surface forces and Reynolds stress. And I will also identify the modified pressure forces term in the momentum equation. I'll do that in a moment. Likewise, in the turbulent kinetic energy equation, I want to identify storage term, energy flux divergence, shear production, and turbulent kinetic energy dissipation. I'll identify those. Also, in the above equations, identify the parameterizations for the following terms: turbulent viscosity, kinetic energy, and dissipation rate. So these are, well, I already said, these are the parameterizations for turbulent viscosity, dissipation rate, and mixing length. Further, I'll show why the advection term in the momentum and turbulent kinetic energy equations have vanished. I'll show why there's no advection in this. Also, which classification of the turbulence model in this simple model is according to. So, I already said this is most likely a one equation model. There is just K equation and 3 equalities to close the rest of the parameters. Okay, so let's begin the fun. Exercise 4. So see, here is my wall flow. This is the surface. X is along the surface. Z is normal. And Y is into the page. Here is my mean velocity. So that's U in angle brackets. Mean or time average velocity. I'm asked to assume Prandtl number is 1, so I assume that. Remember, U is U plus U. V is angle bracket V plus V, and W is angle bracket W plus little w. I was already told that time average velocity in the y and z directions is 0. So this is 0, and that is 0. This by no means indicates that the velocity fluctuations must be 0, by no means. So little v and little w are fluctuating, they're not 0. The other thing is that I said horizontal, something about horizontal homogeneity, so there's no change in velocity anywhere downstream of the flow. So that if I get this profile here, a few meters downstream, I get the same profile. This profile is not changing in the x direction. It's not changing in the y direction either, although the velocity is changing in the vertical direction, the z direction. Just all the same. Also note that there is a pressure gradient that's driving this whole flow. So there's a horizontal pressure gradient. So a couple of things: no change with respect to the x direction. Also, no change with respect to x direction for turbulent kinetic energy. If you remember modified pressure, so let's formulate it. Modified pressure was minus 1 over rho, the density, partial x of mean pressure plus 2/3 of rho k kinetic energy. Remember, this k is turbulent kinetic energy. This k is turbulent kinetic energy, or for short TKE. This P is mean pressure, time average pressure. Mean pressure. And if you want, you can call all of this like tau. Just a matter of notation. So this negative belongs to the formula. Okay, so this is your modified pressure, and you have to add mean pressure to a fraction of TKE to get the modified pressure. The momentum equation let's write the momentum equation. So here I'm just reproducing the equation in the problem. So, which one is the storage term? Anyone want to guess? Left. Which one is the surface and forces and Reynolds stresses? There's only one option. Yeah, this one. So surface forces and Reynolds stresses, and the last option is the modified pressure. Okay, so I label these terms. What about the TKE equation? I haven't derived it yet. I'm just labeling. I'll derive it in the next page. So the TKE equation now this is a little bit more fun. Which one is the storage term? Left. That's not storage. Which one is the, so let me mix it up. Which one is the dissipation term? Last one. Dissipation. I'm also hinting you, right? Because I put a negative sign here. This is a sink. This results in consumption. It's a negative sign there. So this must be the dissipation rate. Which one is the energy flux divergence? Yes. Energy flux divergence. And in fact, if you just look at the math, you can guess it, right? Flux divergence means divergence of the flux, right? Well, this term is very nonlinear, this one. This is raised to the power of 2. By no means this could be a divergence of anything, right? Divergence is this operation, partial z. That's taking the divergence. It's 1D, it's a one-dimensional situation. So there's the partial y, partial x is missing because there's only one dimension here. So this must be flux of something. Divergence of something. What's the flux? Here's the whole flux. And you see, flux is being driven or parameterized using the gradient diffusion hypothesis. Right? And that's the gradient. Right? So using the gradient diffusion hypothesis, this whole thing in the bracket is flux. So that's the divergence of the flux. Okay? And the last term is, anybody want to guess what this term may be called? You had dissipation, you must have production. Or you had sink, you must have a source. So this is a production term. Which type of production? Yeah. I give you two options: shear production, buoyant production. Did I say anything about temperature in this problem? I didn't say anything about temperature. There's only one mechanism to generate kinetic energy: shear. So shear is production. So had I written another equation for heat or temperature, there could have been another term here responsible for buoyancy production of TKE or total kinetic energy. So here are the labeling of the terms. Can you tell me in the two equations, could I have brought the turbulent viscosity out of the derivative or not? Could I bring this out? Or could I bring this turbulent viscosity out? Is it a constant?
It's a function of K.
So it cannot be constant. It is not a constant. I cannot bring it up. If I want to, of course, I can use the product rule and apply the derivative to the term. So derivative of the whole is derivative of the first times the second plus the first times the derivative of the second. I could use the product rule in calculus. But as is, that's how I can write it. It's the most compressed form I can write this. Okay, so for completeness, I'll just rewrite. CKLM, K to the power half, that's the turbulent viscosity. Then epsilon is C epsilon. TKE dissipation. And mixing length. Is here. So do not confuse this symbol here. This is not K. This is not K. This is, anybody knows what this is? Kappa. What's kappa known as? One carbon. So I'll try to sort of write kappa in the sort of a cursive or curly way so you can distinguish. I mean, the leg is twisted here. So that's different from K. So you see, so this is exactly, now all of these are the closed form of the equation. So you see, epsilon here is not closed yet, but I close it down here because I specified based on everything else that I have. Mixing length is not closed yet, right here, right? It's not closed here, but I close it here. Oh, of course, L naught is another constant. So as you might imagine, even a simple problem involving a KL model can be highly complicated numerically. See, there's a lot of nonlinearity in the system of equations. First of all, I'm taking the derivative of something and I'm raising the derivative to the power of 2. This is as nonlinear as it gets. It's pretty difficult to handle this numerically. Well, here too, I'm multiplying one unknown by the derivative of the other unknown. This is a nonlinear term, right? Ordinary differential equations, you just have derivatives added or summed up or together, right? Different orders of derivatives, like second derivative, third derivative. You just add or subtract a bunch of them. That's an ordinary differential equation. But most turbulence models are highly nonlinear. There's also nonlinearity here, right? So you have one unknown, and you multiply by the square root of the other unknown. Very nonlinear. Everything else. So it's numerically, it's a headache to handle this. Although there are lots of techniques to solve this gracefully numerically, which you would do in your labs, computer labs, but this is an example. Can anybody tell me if this is a one equation turbulence model or a two equation turbulence model or an algebraic turbulence model? You got 2, we got 3. Anybody thinks it's a one equation turbulence model? I say one equation. Why? Let's just pause here for a moment. We reserve the term equation for anything other than momentum and continuity. So the first one doesn't count, right? This is always there. But we also reserve the term equation for the differential equation, right? Which this is. So these are not differential equations. So this is for the definition point of view. From the definition point of view, one equation turbulence model. Remember, it's not hard to handle this numerically. I mean, anytime I want nu t, I just calculate it, right? There's no computational cost in finding these other terms. The main computational cost is here, right? To have a numerical recipe to solve this equation. Of course, there's a cost with momentum too, but there's always that cost. Whatever you do, you always have to solve that equation. So we don't count it as the equation to categorize turbulence model. So this is a one equation turbulence model, also known as the KL. Let's derive it. Momentum equation. If you remember, or you recall this symbol, this was always on the left-hand side of the Navier-Stokes equations. It's the derivative of the mean. And by definition, it's partial derivative of respect to time of the quantity of interest. In this case, it's momentum, plus mean momentum vector form, dot product with gradient of the quantity of interest. Remember, this is a dot product. So dot product, that's a gradient and we know how to handle this. So let's label these ones material derivative of mean. Storage. And anybody knows what this is called? Advection. Okay. So if I have u, so let's now expand this. If I have u, vector u, this must be u I plus v j plus w k. So the gradient of u, which is the other one here, is, now I'm not talking about gradient of vector u. You would never take a gradient of a vector quantity. You always take a gradient of a scalar. And if you look at one component of momentum, that's a scalar, right? So gradient of u. But it turns out to be a vector. Because gradient, you take partial derivatives with respect to x, y, z, and each one is in a given specific direction. Partial, again u, y, j, plus partial, again u, z, k. Don't confuse this k with kinetic energy or from Coulomb constant. That's just unit vector k. So I put a hat on top of it. So I have the vector and I have the gradient. Now if I dot product the two, I can calculate the advection term. So dot product, you just multiply term by term, you add up to 0. Okay, so u, it's going to be u plus v plus w is the dot product a scalar or a vector? What does the dot product give you? A scalar or a vector? Scalar, right? So you see there's no I and j or k in this dot product or the advection term. Let's see which terms are 0 on the right hand side. Is u 0? No. Is partial u partial x 0? Yes. Right? This is what I wrote here, right? I wrote it here. Partial u partial x 0. The profile is not changing in the x direction. So, is v 0? Yes, we assumed it to be 0. Is partial u partial z 0? No, it's varying in height. But is w 0? Yes, it is. So you see, the whole thing happens to be 0. So I just demonstrated what the question was asking. It was asking me to show that the advection term is 0. So I just did that. Let's write the TKE equation. Again, I'll follow the same pattern. Material derivative of the mean. Storage term plus advection. Okay, so material derivative of mean storage advection. If you notice, there is a similarity. In any advection term, you always have this vector u. You always have it. Regardless of the equation being for K, epsilon, temperature, passage scale, whatever it is, this is always u, right? Because it's the velocity that advects a parcel of the fluid and takes it around. It could take around a parcel of temperature, or a parcel of momentum, parcel of kinetic energy, whatever it is. So this is always u. And likewise, I can demonstrate to you that this is 0, because gradient of K is partial K partial X I partial K partial Y J partial K partial Z unit vector K. If I do the dot product now, it will be U partial K partial X plus V partial K partial Y plus W partial K partial Z. So let's help me to find which term in each of the three is 0. Which one of the two is 0 here? Partial K partial X. Which term is 0 here? In fact, both could be 0, but anyway, we explicitly assume V is 0. And here, is this 0, this term? No, K varies with height, but W is 0. So the whole thing must be 0. Okay? So these were some demonstration of what would happen to the advection term. Note that I'm using angled bracket for U to mean that I'm looking at the average or mean, ensemble mean of U. I'm not using an angled bracket for kinetic energy. Can anybody guess why? I mean, from notation point of view, why did I not use angled bracket for K? Here's the answer. Because by definition, K is obtained by adding quantities already in angled bracket. Do you remember this definition? So already by definition, K is summed up by adding 3 quantities in angled bracket, or it was already taken mean of, or the variance of. So I don't need to put an angled bracket around K. It's by definition a statistic. It's always a statistic. Okay? So here again is some demonstration. And then this is enough for you to show the equations in the problem. If you really want to understand and analyze fluid systems or derive equations, or even just interpret a problem, you must have the ability to break down the equations and understand term by term what's happening and what the underlying assumptions are. And in this chapter, I have just many problems of the kind where I ask you to show this or that. So hopefully, attempt those problems, you'll be in good shape. So any questions there? And I would say this is where the real innovation is, right? I mean, if you don't have this ability and just drop down menus on different sort of solvers and hit run, sure, you get an answer, but you don't appreciate the underlying effort behind the model when it works and when it doesn't work, right? So nobody wants to do monkey work, when they do fluid simulations. I mean, if they're good engineers, scientists, right? So that's why I always push for the fundamentals and an understanding of the underlying equations. And again, that's where the innovation lies. When you understand these equations well, you can develop your own models and solve them. And that's where the real money is. Or sort of cutting edge in technology and pushing a career forward in fluids engineering or whatnot. So let's talk about large-eddy simulations. So large-eddy simulations, this chapter is much shorter than the other chapter. I only have maybe a few pages. But for the right reasons, because the large-eddy simulation builds on top of the turbulent viscosity models. So what I have to add on top to teach this model is much less. So I can do it in maybe 3 or 4 pages. In large-eddy simulations, as we said, the larger three-dimensional unsteady turbulent motions are directly presented, resolved, while the effects of the smaller scale motions are modeled. So here in this type of simulation, you exactly determine what happens to a time-varying large scale fluctuation. You actually resolve itself for it in the transient sense. But smaller scales you can't, you still model them. In terms of computational expense, we already said that LES, large-eddy simulation, lies somewhere in between Reynolds stress models or turbulent viscosity models and direct numerical simulations. So it's neither too easy nor too difficult from the point of view of computational expense. It is motivated, in fact, by limitations of each approach. In addition, for many applications, most transport mechanisms occur at large scales. And I talked about this last time. It's the large scale that drives physics of a lot of problems out there. Like if you take air pollution, for example, it's the large scale movement of air that results in air pollution. I told you about the inversion cap. So is heat transport. When there's a heat wave in the atmosphere over a city, it's a large scale phenomenon. Right? So large scale is the real deal, and that's where you want to spend your computational effort to understand. So this justifies simulating large scales accurately while modeling small scales. So from a theoretical point of view, large scales of turbulent motion are dependent on geometry and conditions of the flow, while the small scales are universal. If you like, go back to chapter 7, we already said this, that smaller scales are isotropic. No matter what the geometry of the flow may be, flow over a building, in a pipe, in a turbine, in a pump, larger scale depends on the geometry of the flow. Let's say in a pump, the flow would circulate, swirl, right? But smaller scale, they're all the same. Flow around a cube, in a pipe, in the atmosphere, in the ocean, it's the same. So there is some universality in small scale, which makes it easy to formulate and close a turbulence model, or simulation in this case. Okay, so all of these are enough evidence and motivation to do LES. LES was pioneered, I would say, in the 60s and 70s by two of my role models, Smagorinsky and Dierdorf. Both of them were atmospheric scientists, so they developed LES to be able to simulate the atmospheric transport for applications in weather forecast and climate research and things like that. Now, let's get into the bit of mathematics. LES requires 4 computational steps, and I will explain to you these 4 steps. The first one is called a filtering operation, in which case you decompose the velocity, the same instantaneous velocity you had in the previous chapters, it's the same velocity field, both as a function of time and space, into the sum of the filtered or resolved component, U bar, and the residual or subgrid scale component, U prime. The filtered velocity field then differs from the mean, because remember, mean was obtained by ensemble averaging. You repeated the experiment many times, and this will give you a mean. Here you're talking about the filtered velocity. Okay, it's not mean by any means. If the filtered velocity can change. Okay, I'll demonstrate with enough details in a bit. Because the filter velocity is, as I said, time dependent. Remember, the motion of larger eddies are simulated. The time dependent. A large eddy comes and goes, right? Slower and faster, smaller and bigger. So there's no reason why the filtered velocity U bar should be constant. It's not. It's time varying. And that's the essential difference between this and Reynolds averaging or time averaging or ensemble averaging. Okay, so this is how we show. So if you like, so I'm gonna repeat writing this up here. Remember, in Reynolds decomposition, you did this. Reynolds decomposition. You had U, velocity field U, expressed as the sum of the ensemble average plus fluctuating. So if you like, so ensemble average, if you like time average or time fluctuation for the second part. Time fluctuation. Ensemble average is the first term and time fluctuation is the second term. That's how you decompose by Reynolds decomposition a signal. However, in large-eddy simulations, it's still the same signal U, but you show me U bar plus U prime. It means totally different things. This is now a spatial, if you like, a spatially filtered. It's still time dependent. And U prime is called sort of, if you like, a spatial fluctuation. And both are still time dependent. So okay, so it's different methodology or approach in decomposing a signal. So what I need to say is, be careful with the notation. A lot of the textbooks you open reserve overline for ensemble averaging and prime for time fluctuation. A lot of books have that. But here we're doing the opposite. We say angle bracket represents ensemble averaging and small lowercase symbol represents time fluctuation. So be careful of the textbook you're reading or, I don't know, article you're reading. Be careful of the convention. Okay, so what is a spatial filter? So now I want to demonstrate this with a sketch. Everybody is comfortable with the idea of time averaging, right? Or ensemble average. You repeat some phenomenon and you take some sort of statistical average. Same idea can be done in space. Averaging doesn't have to be done over time. It can be done over space. So spatial filtering concept. Let's suppose I consider a water bottle. If you look at a water bottle, it has many fine features. So this is the cap of the water bottle. Then this is the body of the water bottle, so most of them have. So this recess. This is a water bottle. I guess for manufacturing reasons they design mini grooves in the shell. It's not bad. If I spatially filter this water bottle with a filter length, let's say if I apply a very short filter length of this much, but that I show by this arrow, and I spatially filter this. Do you agree with me that the water bottle should appear more simple? Probably if I spatially average, all of these mini grooves are disappear, right? Because I'm filtering over that length. So if I do that filter, the water bottle will look like this, probably. Maybe that's good enough, right? You still agree with me that for many purposes, whichever bottle I gave you, you would drink from it, and that's a good realization of the water bottle, right? But if I apply a very large filter length, let's say now I want to apply this length, what should the water bottle look like in this case? Like an egg. Yeah, or something like that. See, now the smaller features are no longer distinguishable. I mean, this length cannot preserve the geometry of the cap. Make sense? So spatial filtering is the essence behind large-eddy simulations. And I can tie this to a boundary layer flow. Like a real boundary layer flow looks like this. On an average sense, the boundary layer flow, the mean or ensemble average looks something like that. So this is X, this is Z. Boundary layer flow. But by nature of the physics, this is going to change. Like it changes second to second. 1 second, it may look like this. So this is the instantaneous profile of the velocity. The next moment, it may look like this. And the next moment, it looks like maybe this. So from each moment to the next, it changes. What you would do in large-eddy simulations, if you capture the transient features of this boundary layer at only the large scale above a filter length. If you simulate this in this grid, let's say that's a two-dimensional grid you use to simulate this flow. And I'll make it finer. Now you have a grid, and you want to simulate this flow in the transient way. The size of the grid, so this is the filter length, right? This is the spatial filtering that you apply to the velocity. If you did that, you would lose the very small features of the flow, which means that you would only capture the large scale fluctuations. So this one would look like maybe this. This one would look like. So this would be, still the time average the same, but your simulation is no longer steady, right? It's transient. From moment to moment, the large scale field changes. So if you like, this is now U over bar at different time instances. And in the terminology of large-eddy simulations, we call each one a realization. So that's, let's say, realization 1, realization 2, realization. And in each one, still, I can claim U is U bar plus U prime. So large simulation gives you many realizations. And you can't just take the answer and say, give it to your boss and say, here's the 1,000 realizations. Go figure it out. No, you're not finished. Now you have to do some statistical work, maybe take the averages of those realizations, do something. Calculate the variance. There's always post-processing involved. Okay, so now we are in good shape understanding the issue of spatial filtering. Let's go back to our steps and show you the rest of the steps required. In the second, the Navier-Stokes momentum equation can be developed. Now for the filtered velocity. Okay, now the equation is the same, physically, but it's now applied to the filtered velocity momentum. This equation will contain residual stress or a subgrid scale tensor, or SGS tensor. And now this is the term that must be closed. I'll show you in the next page in a bit. The third step is that the Navier-Stokes momentum equation must be closed by modeling the residual stress, or SGS tensor. Remember, the closure problem, right? There's always one term you don't have an equation for it, so you have to close it. Basically, bring constant out of your pocket and be inventive and close that. And you still do that. And finally, the model equations are solved numerically now only for the spatially filtered one, which provides an approximate solution for the large scale motion or the realization. And in my picture I showed that to you. So these are the 4 steps involved. So now what I should do is I should explain in more detail what the second and third steps look like. So that will be the next step. Now something about filtering. Well, if you talk to an empiricist, say, okay, what is a filter? Say it's a piece of paper, and you put flow or air through, and you capture some large-scale particles or contaminants from a filter. Well, that's what a filter is, right? If a filter is only lets fine stuff go through and sort of blocks the impurities for any sort of application. That's a filter as we understand it. But mathematically, we can also define filter. Mathematically, a filter gets rid of, now does the opposite, the smallest scale fluctuations. That's what the mathematical filter does. And if you think about it, integrals are filters, mathematically. Integral is a filter, because it gets rid of the fine scale. If you take the integral of anything, you lose information. Agree? You lose what happens in between. It just gets the overall area under the curve. So mathematically, the filtering operation is described by integrating a function towards the entire domain. For turbulence and for LES, we need to spatially filter the velocity field. And we do it in this way. In fact, the spatial filter is the integral of the velocity vector given some filter function. This g is a filter function. So you multiply the filter function by the velocity, integrate it over the entire space. And in one of the computer labs you'll do this. I think it's the very last lab. The specific filter function g is this. It must satisfy the requirement that the integral of g over the entire domain must be 1. I mean, the analogy is the probability density function, right? The probability density function, the property of it requires that integral of any PDF should be 1. And then you multiply that PDF by different variables and you calculate mean, variance. Remember the third lecture there? So it works somehow like the probability density functions. Let's show you a very simple filter called the box filter. The filtering operation, suppose you apply it to a one-dimensional field u. It's only one component of velocity u, only in the x direction. The box filter is the simplest filter known, results in the average of u in the vicinity of the filter length. Let's say if the filter length is delta, 2 centimeters, right? I mean, if it makes it easier, this is the filter length, right? The length of averaging. So here delta is larger. Okay, so delta is the filter length. You just take the average of the function in that box and move on. So if you're close, the vicinity of the filter, let's say you're 1/2 of the width of the filter from either side or from the center, you just take the average. Otherwise, 0. Okay? So that's a very simple filter, box filter you can apply. And large-eddy simulations do it. They assume that the velocity is filtered over some space. Let's talk about the field conservation equations. Now, I should do the second part, as promised, to show you the Navier-Stokes equation. By applying the filtering operation to the Navier-Stokes equations, we can obtain the governing equation for now the filtered quantities. Again, we spatially apply, when spatially uniform filters are used, such as the box filter, the filtering and differentiation operations commute. Which means that if you have, remember, filter is like an integral, right? You can take integral inside and outside of various mathematical operations. So the filter, if you like, the filter or integral of a derivative is the same as the derivative of the filter. Which allows you to filter the continuity equation. So this is the continuity equation. Remember Einstein notation, I repeats, so this is du dx plus dv dy plus dw dz, right? You filter all of that is the same as partial of the filtered velocities. which should mean that the continuity equation also applies to the filtered velocity. In the same way, it must apply to the subgrid velocity or U prime, SGS or U prime, but the portion that was modeled, that's not resolved. That also applies. So continuity would apply to both the filtered velocity and the residual velocity or the subgrid velocity. So with these considerations, the momentum equation can be given as follows. The same equation you've seen before, right? You have the storage term, you have the advection term, you have the surface forces, and you have the normal and body forces. But now you are filtering each term. Filter that, filter this, filter this. Everything else is easy except here. Here you're taking the filter of a product of a pair of velocities. Okay? So this is where the turbulence closure problem manifests itself. Why? This equation needs further attention because the filter of a product is different than the product of the filter velocities. This is what you want. I mean, this would be, if in place of that, I had this in the equation, it would be easy, right? Because I had a fully specified transport equation and I solve it with some numerical technique. But as long as I have this, the job is not done. This is problematic. This is what I want, right? So you have to resort to your knowledge of mathematics. This is what you want. This is what you have, right? So the residual left over in the equation is residual stress tensor. In other words, if I want to replace this by this, I can do that, but as a result, I get a residual stress left in my equation. Okay? And this would look very analogous to when we did it for Reynolds averaged equations. There we had this one in the equation, remember, right? But we desired that one, so the Reynolds stress tensor was left, and then we formulated parameterized it. Here, something else happened. This was left in the equation, not that one, but it looks very analogous, very similar. So it is analogous to the Reynolds stress tensor when we did it in chapter 4 or 5. Just a matter of notation, you can also separate out the isotropic and anisotropic pieces. So here is residual stress tensor for components I and j, right? Tau ij, when I put superscript r to specify residual because I don't want to confuse it with Reynolds averaging. Here I'm just saying if I'm looking at the same component I can call this residual kinetic energy. And again, Einstein notation, that would be residual stress tensor in summed up over x, y, z. Okay, so just terminology, and then I can separate an isotropic part in this way. So I can express the anisotropic residual stress by the total residual stress minus the isotropic part. Again, very analogous, similar to what we did in the other chapter. And as usual, I absorb the isotropic residual stress in the pressure, and instead of pressure, I get modified filtered pressure. Again, we did this in chapter 4. Here was the filter pressure, or back there it was ensemble average pressure. Back there I added kinetic energy to it, or a fraction of kinetic energy. But here I'm adding the fraction of the residual kinetic energy, and I get modified filtered pressure. So to distinguish the difference, I put a little m here, and I overbar. So this means modified filtered pressure. And then my momentum equation would look like this. So now I get what I want. Now I have a product of Ui, Uj. But as a result, this new term popped out. So this is the closure problem. So the anisotropic residual stress force will remain, and I have to close it. And that's what I'm going to do. So again, the material derivative of the left-hand side is the same as what we've been dealing before. So this is the left-hand side of that equation. That's not a problem. I can do it. But what happens to the residual stress? Residual stress now is modeled using the Smogorinsky model, which is really nothing but turbulent diffusion hypothesis, right? In subgrid scale, the model part, it's like a RANS model. In the subgrid, it's like a turbulent viscosity model. It's not any different. So over there, I can just equate the residual stress, the anisotropic part, to rate of strain. We've done this before, right? This is not new. And then I have a constant of proportionality, like turbulent viscosity. But this time, I don't call it turbulent viscosity. I call it residual eddy viscosity. So S bar was the filtered rate of strain. So you've seen that before. And then finally, to close my model, I should parameterize the residual eddy viscosity, which I can do gracefully. Now this appears like a mixing length model, right? You can assume mixing length LS multiplied by characteristic filtered rate of strain, and LS is a model constant. So this is where I put my hand in my pocket and bring a new constant, close the model, and there's another constant there, CS, 0.09, which you can parameterize. But what about the filter length? What is the filter length? Well, the filter length is the local geometric average of the grid. Remember, in any turbulence simulation, numerically, you have a grid somewhere near the wall, on the top, in the middle of the domain. Well, this grid has specific dimensions. Z, and dx, dy, or delta z, delta x, delta y. If you take the geometric average of the sides of that numerical cell, this is your delta. I mean, if you like, delta is somehow overall the size of this, the local grid cell. And now you see, why am I saying large-eddy simulations are not complete models? Because if you change the grid, delta changes. Agree? So delta, if you change the grid, delta changes, residual viscosity changes, everything else. So it back propagates into the whole modeling system. So large-eddy simulations are grid sensitive. They're not complete. They're incomplete. And if you coarsen the grid, something happens to them. If you find all of the equations change, the scale, the filter length change, which means, I mean, an analogy is this. If I run a very fine grid, the model gives me this. But if I coarsen my grid, the model gives me this. See, it's very sensitive to grid and anywhere in between. So you have to be careful and choose a grid that's best for your needs. Okay. I mean, I really don't have much more to say about LES. I mean, the equations are the same, the solvers you use for them are the same, but they're just transient, and you just treat larger scale and smaller scales differently. You actually solve the equations as a transient flow. It's the same Navier-Stokes equation, nothing is different. You just solve it in transient mode, and you obtain a time-varying solution. But you are aware that a smaller scale is being modeled, is not being resolved. Okay, so it's always a transient simulation. And this came up in Scott's thesis defense, remember? So he ran a RANS model, very high resolution RANS model with transient mode. And I was convinced that he was actually showing me LES results. Do you believe me? Having told you this, now you were doing LES on subconsciously or unwantedly, maybe wantedly, right?
Yeah.
It's very hard to say what you're doing, usually, right? Depending on what lens you view your actions through, right? You could be running RANS by LES. Some people run LES, but they're actually running the RANS model because they make oversimplifications and then do averaging all over the, like right out of the bath, and then use a very coarse mesh. So things get really shady quickly into the unknown. So be careful of what you're doing. So there is also a lab on LES, computer lab, so hopefully you can enjoy that. And next time we will do the problem. You're running out of time. Any questions? Sounds good? Okay, so we'll see you next time.